Something quiet but historic is unfolding above Earth, and most people still think of it as just another space telescope. The James Webb Space Telescope is often described as powerful, revolutionary, or game-changing, but none of those words fully capture what is happening now. Webb is not just collecting better data, it is actively reshaping how NASA defines discovery itself. The telescope is revealing that the universe behaves less like a carefully balanced machine and more like a restless system that keeps generating complexity wherever physics allows it. When NASA launched James Webb, the goal was not to search for aliens or confirm science fiction ideas. The mission was far more precise and in some ways far more ambitious. Webb was designed to look deeper into time, to analyze the chemistry of distant worlds, and to test whether our models of cosmic evolution actually hold up when exposed to real data. What scientists did not anticipate was how quickly those models would begin to strain. What Webb has already shown is that many of our assumptions were built on limited evidence. We understood planets primarily through our own solar system. We understood galaxies through indirect measurements. We understood atmospheres through rough estimates. Webb has replaced estimation with measurement, and measurement has a way of removing comfort. One of the clearest areas where this shift is happening is in exoplanet atmospheres. Before Webb, astronomers could infer the presence of an atmosphere on a distant planet, but they could not examine it in detail. Webb changed that almost immediately. Using infrared spectroscopy, it can detect specific molecules as starlight passes through a planet's atmosphere during transit. Water vapor, carbon dioxide, methane, sulfur compounds, these are no longer theoretical possibilities, they are measured signals. NASA's next focus is not simply detecting these molecules, but understanding how long they persist and why. According to older models, many close-in planets should lose their atmospheres rapidly due to stellar radiation, yet Webb keeps finding thick atmospheres where none should survive. The logical next step is long-term monitoring. Webb will revisit the same planets repeatedly, watching how their chemistry changes over time. If these atmospheres remain stable, then something inside these planets must be actively maintaining them. That realization forces a deeper question. Planets may not be passive objects slowly eroded by their stars. They may be active systems with internal energy sources that drive geology, chemistry, and atmospheric renewal. Tidal heating, radioactive decay, and interior convection are now being treated as central factors rather than secondary details. Webb's infrared sensitivity allows scientists to detect subtle thermal signatures that point to internal heat escaping into space. This matters because it expands the range of worlds that can remain interesting for billions of years. A planet does not need to sit in a narrow, ideal location around its star to stay active. It needs energy, and energy can come from many sources. This is one of the most important lessons Webb is teaching NASA as it plans future missions. Webb's influence extends far beyond planets. When the telescope began observing the early universe, it revealed galaxies that appear far more mature than expected. Some show organized structure, high star formation rates, and chemical enrichment at a time when the universe should have been relatively young and chaotic. According to standard cosmology, galaxies need time to grow, merge, and evolve. Webb is showing that many galaxies reached advanced stages astonishingly fast. NASA's upcoming Webb observation cycles are now designed to study these early galaxies in detail. Astronomers want to understand how quickly stars formed, how efficiently heavy elements were produced, and how early black holes influenced their surroundings. If these galaxies are common rather than rare, then the timeline of cosmic evolution must be adjusted. The universe may not have taken a slow path toward complexity, it may have accelerated almost immediately. This ties directly into one of Webb's most unsettling contributions, the study of early black holes. Webb has detected active black holes with masses millions of times that of the Sun at epochs when the universe was only a few 100 million years old. Traditional models struggle to explain how such massive objects could form so quickly. Slow growth through accretion does not seem sufficient.
NASA is now using Webb to test alternative scenarios, including direct collapse models, where massive gas clouds form black holes without first becoming stars. If confirmed, this would mean the universe developed shortcuts to complexity early on. It would also mean that black holes played a significant role in shaping galaxies from the very beginning. closer to our own cosmic neighborhood, Webb is changing how NASA thinks about planetary systems as a whole. Rather than studying planets in isolation, astronomers are increasingly examining entire systems to see how different worlds respond to the same star. Why does one planet lose its atmosphere while another retains it? Why does one become geologically inactive while its neighbor remains dynamic? These comparisons reveal underlying rules rather than one-off anomalies. Another frontier Webb is opening involves planets that exist far outside traditional definitions of habitability. Some worlds receive intense radiation, others receive very little stellar energy at all. Yet Webb continues to find chemical activity in places that were once dismissed outright. In some cases, internal heating may dominate over stellar input, allowing planets to remain active even when their stars provide minimal energy. NASA is particularly interested in this possibility because it radically expands the number of potentially long-lived worlds in the galaxy. A planet could remain chemically active long after its star begins to fade. In some cases, planetary evolution may be partially independent of stellar evolution. Webb's data is forcing scientists to take that idea seriously. One of the most careful and deliberate aspects of Webb's mission involves chemical disequilibrium. Webb has detected atmospheric compositions that should not persist under stable conditions. Certain gases react with each other and should disappear over time, yet Webb observes them coexisting. This suggests ongoing replenishment or regulation through physical or chemical processes. NASA is extremely cautious here. Chemical disequilibrium does not mean life. Volcanoes, photochemistry, and interior reactions can all produce similar signatures. Webb's role is not to declare biology, but to identify environments that are dynamic rather than static. These are places where energy flows, matter cycles, and chemistry remains active. That distinction is critical. Webb is not finding answers, it is finding conditions, and conditions are the foundation upon which all complex systems are built. As these discoveries accumulate, NASA's long-term strategy is evolving. The search is no longer focused narrowly on Earth-like planets around Sun-like stars. That approach now appears overly restrictive. Webb has demonstrated that complexity does not require familiar conditions. It requires persistence, energy input, time. Future missions are being designed to complement Webb by observing planets over longer timescales and at higher resolutions. The goal is not a single dramatic detection, but a growing statistical understanding of how common active worlds truly are. Webb is providing the framework upon which that future will be built. Perhaps the most profound change Webb is bringing is philosophical rather than technical. For decades, the central question was whether the universe could produce life. Webb is suggesting that this question may be incomplete. The universe appears to produce complexity readily, over and over again, in many forms, under many conditions. This does not mean life is everywhere. It means the ingredients and processes that make life possible are not rare exceptions. They are natural outcomes of physics and chemistry interacting over time. That realization changes how scientists interpret the apparent silence of the cosmos. Silence no longer implies emptiness. It implies that outcomes vary even when processes are common. James Webb has not overturned science, it has refined it. It has shown that our earlier models were not wrong, but incomplete. They were based on limited data from a single planetary system and a small observational window. Webb has widened that window dramatically. As the telescope continues its mission, one thing is becoming increasingly clear. The universe is not fragile. It is not finely balanced against complexity. It is resilient, adaptive, and surprisingly efficient at building structured systems. Planets endure, atmospheres persist, chemistry refuses to settle into equilibrium. So when we ask what NASA hopes to discover next with the James Webb Space Telescope, the answer is not a single object or moment. NASA is searching for understanding, for rules, for patterns that explain why complexity keeps emerging in places we never expected. James Webb has not told us that we are alone. It has not told us that we are surrounded. What it has told us is far more unsettling and far more profound. The universe is capable of building, sustaining, and repeating complexity across vast scales of space and time. And as Webb continues to observe, one realization becomes unavoidable. The unimaginable is not waiting somewhere in the distant future. It is already happening, quietly, relentlessly, across the galaxy. And this is only the beginning.